Good morning, everyone. As maybe some of you have seen, the room was occupied by some Polito events of welcome days for students. So, as agreed upon, we are doing this class online. First of all, as usual, I will do a quick fast forward of the last week. So, we have seen the majority of details about coroutine, which I remind you are a higher level abstraction to execute in a more concise and also convenient way the concurrent programming in the Kotlin world and in Android. The core idea is to separate some sprint of your function to execute eventually on classic operating system threads or onto the let me share the screen. Okay. So either on top of operating system threads or custom threads that you may explicitly invoke by, for instance, creating custom dispatchers and assigning the thread coroutines to each threads of the pool, or to use a dedicated pre-baked dispatcher into your Kotlin application. We've seen that there are special scopes, which are the context, part of the context in which your coroutine are allowed to execute, because you cannot launch straightforward coroutine from a plain function. You have to resort to a scope to either launch a fire and forget coroutine or to initiate an async await model. And there are four scopes that are provided by the Android world, which are the main scope, which automatically allows you to assign the coroutine to the main thread dispatcher for the UI. You have also the view model scope, which is devoted to the view model, the life cycle, and also we have seen the remember coroutine scope, which is which purpose is to use in the composable Jetpack Compose world. We've seen that there are four main, actually the three main that you will mostly use are main. You have just one thread, IO with about 50 thread used for interfacing with the disk and network IOs, and also default dispatchers, which is usually uh, you usually exploit it for CPU intensive work like the one that you used to do in threads, in classic threads. You can also swap context during the execution using the with context suspend function. And then other important stuff that we've seen that you have to design and program your function, suspendable function to have that should be executed in coroutine with cancellation in mind. So you should be cooperative by eventually foreseeing some place if these are not by given by granted, if any suspension point is already available into your coroutine into your special suspendable function to explicit some points in which to ensure active or yield for somebody else to eventually kick in the uh, orchestration process. We have seen that there are two main jobs kind. The main job which allows you to keep track of all your sibling and also react to eventual cancellation of your sibling. And there is a supervisor job which allows you instead of keep your coroutine alive, even though if one of your siblings fails. And as maybe you may remind, we still are talking about concurrent programming. So even though there is a simplification in terms of synchronization mechanism, you still have to rely on mutex and semaphore should you go for some dispatchers which allows your execution on multiple threads or if you don't want to constrain the parallelism of your coroutine to execute on multiple threads. We have seen that mutex and semaphore in the context of coroutine are just other kind of suspension points, so the deadlock will be not, let's say, blocking for the application, but still it's good to remind that mutex is not re-entering, so try to avoid introducing deadlocks into your code. Okay, I think that that is all the key stuff. We have also seen that in the context of a routine used inside composable objects, you are allowed also to have an additional result class, which is able for you to aggregate and encapsulate data as a result of work executed inside a remember a coroutine scope of type remember, which will be hosted and retained by the view model or the better to say the composable object. And we stop more or less here. Any question so far about the coroutine or even just the laboratory's assignment, lab 2? Feel free to use eventually the chat or just speak. Okay. So to better recap, as I promised you, I would like to do a quick live coding with kind of stuff that we see in the context of UI. So let's take Android Studio and I will create a new class here. Let's call it demo, and I will recycle the interface of the counter that we have used for the basic thread demo. So just copy this piece of code, renaming some methods. This would be not here anymore. If I could forget about that. Okay, nothing too important. Let's see if just it runs on the device. Mhm. Really, good luck. Here. This is the old one. Let's see if now it works. Hold on that. Okay, what I want to do as a example now is to let's say, try to have some counter, which instead of just incrementing the value by one immediately, to do that after some delay is introduced. Okay, so the most simple thing that we can think to implement would be like that. I will fix that in a second, just to keep on with the process. So instead of having a thread here into the uh, button on click, I would rather have the implementation of this increment in our coroutine counter as count plus plus prefixed by some delay of, I don't know, 3 seconds. Let's make it 2 seconds. And we have to make this method as suspend method. Then, as soon as we make it suspendable, something will be told to us in terms that we cannot simply run our suspendable method via the on click, since it used to be via suspendable file, so we need some scope to run it. So either you can, let's say, create some straightforward scope, like run blocking or stuff like that, or coroutine scope. But I've told you during also the recap that is better in the context of composable to also retain the intermediate result in your views to resort to some remember coroutine scope, which I initiate here. Okay, remember coroutine scope. I don't want to decorate the context furthermore, and here I go for simply scope dot launch dot increment. Oh, yes, of course, I forgot here to um, rename. It's kind of a stretch. Correct. Mm, very strange. Mm, Let's force it to make some recompilation. Why it's running this one? I don't know. Okay, let me delete this class for now. the same package. And see, for no reason, it was launching the previous one. So as you can maybe notice, after I click increment, the UI is not blocked, and after 2 seconds, now we will receive the update here on the UI. Cool, but not the best, uh, let's say, approach as in, let's say, in the idea of making your code grows in time and in complexity. Because, for instance, here you don't have maybe the control over which explicit control over which scope, or better to say, over which dispatcher your increment will be executed. We have, let's say, encapsulated the scope launcher inside the composable, so we ensure that block will run on the main dispatcher, but maybe somebody else using this view model will not be so convenient to say that this will run eventually in a composable thread. So one thing that you can maybe uh, speculate to implement as a slightly version increment version 2 will be like, instead of having suspendable function, to encapsulate here the uh, the coroutine scope, and since we are in view model, we can maybe leverage the view model scope. We execute this code, and since we are just going inside straight into inside of this execution, we can use the single expression. Something like that. So if we use that approach, I may not need the scope to launch, but maybe some of you should complain about the fact that this should not run appropriately. Let's see if maybe works, but it's not the best because we have not enforced the execution into the main thread somewhere in these flows of execution. So maybe run again. Okay, so how this is happening? Because actually the view model scope is able to, being that interface with the composable world, is able to cope with that. But as I said, it would be better to explicit the dispatcher on the main context. One way could be to go for, of course, resuming the scope here of the remember coding scope, but also to create another, say, call it uh, not so better increment, in which we define a coroutine scope maybe with some, oh, that one, coroutine. Okay. With dispatcher main and job as job. In that case, it's better to move the dispatcher main into the launch method and then just use the job here. Problem with that is that you lose the, say, the facility of observing that this middle will be a middle with some suspend inside, and also you create maybe some coroutine with overhead in terms of a thread that will be actually not used because we have to execute it into the main thread. So if I can still go here and do like vm dot not so that increment. This could run eventually without stopping the button click. Still works, but from the point of view of say good code design is not good because we lose track of the fact that this will be invoked in some suspendable method, and also we lose access in that way. We may lose. It's not mandated to run into the remember coroutine scope. So we can do the last mile by making this a suspendable method, which runs still on the main thread. And then I will do that by simply doing what? So to have a sustainable widget, we need some just, as we have done in the first step, some suspendable function to expose the suspendable keyword without creating from scratch a new context coroutine scope here. You remind which is the method that is actually a suspendable function that ensures us to execute in some dispatcher. Is the with context. Okay, if you go with the with context for a better increment, now we'll be asked to make this method suspendable because there is no more coroutine scope executing the suspendable part, and also we will be forced to encapsulate this into the remember coroutine scope. Otherwise, we will not be able to execute these methods. So we get the best from both worlds. So here we have masked the complexity of dealing with, okay, I need to ensure that it's run on the main thread. So eventually, if in this will be called from some other places, you will still be fairly sure to run on the main thread, but at the same time, you don't have to retain this complexity of carry on all the stuff to remind when your code grows. So that could be a better approach also for your projects. Any question about this pattern for composable with coroutine? So host, hoist the remember coroutine scope, which will be used to launch several eventual methods to update values into the composable. And then should this method be designed, for instance, in the view model, it's better to make it suspendable to not lose track of suspendable method by single expressing the with context. Okay, if no question, let's continue to discuss and finish our discussion actually today about the coroutines. There are just a few remarks that we need to know about the coroutines, and it's about how understanding how they are manipulated in terms of transpiling from the compiler, just to close the loop and be able to overview all the process of coroutines. So we have said that the um, behaviors, sorry to receive a message. The behaviors of coroutine is to create an abstraction on top of the thread word with this suspendable function, but actually the way in which let's say we under the hood this process should be handled may differ based on the kind of thread is hosting your coroutine. As maybe you remind, we have either a pool thread that can come from the pool, a thread that can be, let's say, created by straightforward creation of a thread in the in the Java library or Kotlin library. And then we have also the Android world threads, which may be hosted on a looper handler with message queue. And these three ways should be able to handle with transparency from the point of view of programmer. So under the hood, what the Kotlin and the transpiler does is that if some coroutine is assigned to a thread that was belonging to a thread pool, it will be eventually release, keep the thread and give it to other coroutine, eventually from the same dispatcher context. If there was a dedicated thread that you run, it will become useless, but actually the Kotlin library will put in place some mechanism to not make waste of resources. And if you have the looper, for instance, for the main thread, this will be fetched as a next task to execute in the message queue. So the main, let's say, the main two differences are between the thread pool and the looper mechanism. You remember maybe that the also that when you create a thread, you have a lot of stuff that moves between the stack and the heap, and a naive solution to preserve the state of the execution, which also means the local variable and also the point, the address, the line of code to simplify, in which you have to resume your execution should be also somewhere. So you may think, okay, let's just uh, pack all these data into some heap allocated object and then push on the stack the return address of the code to execute reason time. But of course, this will create a lot of overhead in our code. So the idea, the solution that was found by the uh, people in Kotlin, in the Kotlin world, was to instead implement the so-called continuation passing style. What is that? Is the idea of, let's say, recomposing, manipulating your methods, your suspendable methods, to be like in the form of a state machine. A state machine which each suspension point may become a state of your virtual machine. So each state will be then the equivalent of the return address to come back later. So you will, let's say, have just a transition to states which are execution point into your inner class. And this is why in this slide it's called that the The return address is actually just a label, an integer label, because you say the first suspension point, the second, the third, and so on and so forth. And this partial execution will be able to preserve across the suspensions their data by using a so-called continuation of interface object. So an object that implements the continuation interface. What is this continuation interface? We'll see in a while. So just to remark that in this approach, you have no more let's say, some code to execute after the function. You have just one function which will be encapsulated into this continuation interface with several states to reference instead of pushing and popping from the stack the return address. And then also you have for each of the sub functions that represent a sprint within the suspension point, there will be no return, but state transition. Let's see how his continuation interface implemented. So you have a resume with which is the method to operate the state transition, and also you need to preserve the coroutine context. That is essential, for instance, if you think about the with context. So without preserving the coroutine context and eventually have a different continuation to pass with a different coding context, we will not be able to operate the context switching inside the same state machine. So that's why each continuation holds the coding context. If you have time and curiosity, you can also try to create some very simple methods in Kotlin, as we have done here with a suspendable function with two parameters. And if you compile it and then decompile the DEX file, you will notice that into the Java bytecode or into the, let's say, decoded reverse engineered Java, there is this continuation object that will be added for you without you knowing it. So you will not see, but the compiler will add as a last parameter this continuation object into your suspendable method. So suspend will be basically translated into add some continuation as a method at the end. That was stuck. Bear in mind that the approach of continuation should have and will actually allow you to execute your code not just asynchronously, but should support also the execution as a synchronous in the same thread. So both the behavior of going to a function and to the next sprint inside between two states, to suspension point, and then go back to the main one, or execute some piece of code and suspension point into another thread, both of them should be supported by the continuation passive style. Okay, we have seen that. Okay, as a number of suspension points that are inserted into your state machine, you will have like n plus one states because there is an additional states that need to, let's say, host the process of the several state of the virtual machine. So you will have like if you have three suspension points, you will have actually four states to into your transpiled method. So what to remember is that in the coroutine world with the continuation passive style implementation, the continuation is actually just a closure that hosts the coroutine current state, which is the last execution point or the last address you may uh, link back to your knowledge. the set of local variables that will be needed inside each suspension methods, the results of previous computation, which may not be the same thing, and the callback that should be invoked when the sprint terminates. So methods, in that case, we mean at the end of each state transition. And remind that you still have the coroutine context. So you have the dispatcher, the job, and the exception handler eventually to propagate. Let's see some example from a lightweight snippet of code of how this transpiling will operate. Beware that this is actually just a pseudocode. The real code is much more complex, let's say, unreadable from the human point of view, but you can look for yourself. So in this method, we just want to fetch some data and store it in a local variable, and I use this variable passed into the process data method and show via this intermediate R local variable into another window to display data without returning any result. So if you look for the fetch data where this is stored inside our continuation, you will see that this is inside the resume with method, which is the transition state that I told you before. Inside this resume, you will have the switch case in the word of code, which is the when on the label. There are how many labels? Three labels, even though we just had two suspension point here. So we had an additional one, which is the one that you may consider about the show data. Okay. So this fetch data will be hosted in a temporary variable. And eventually, if the coroutine is suspended, we return or will transition this to another label one. Okay. And the data updated in the temporary result that will be passed to the other method. You do almost the same, and if you look very thoroughly this code, you will see that the R is actually not hosted as a local variable into the continuation. Why is that? Because for D, you need this to survive two-state transition here. As you can see, this result should be hosted and survive across a different state transition, whereas for the result, it will be able to go straight by passing the temporary parameter into display data. Okay, so it doesn't mean that every variable that you have will be also hosted. There is some optimization going on, and there is the label that will be able to execute the state machine to retain the state. The most awake of you should also have noticed that this code may seem like a recursion happening, but it's not the case. Remind that this is just a pseudocode. So this resume with inside the resume with is just a simplification of more methods that will allow to have the external resume with a state transition inside. So there is no recursion occurring inside the continuation. Otherwise, it will not be possible to execute in a synchronous way all the stuff that we need. So as a final remark to remind, it means that by what we've seen, the suspendable means that you will possibly suspend your execution, but not centrally suspend the execution, unless you want, if you want guarantee that you will, as a suspension point will effectively suspend, you have to use one of the two methods, which is delay or with context, which are the only two which will be enforced to always suspend your coroutine. Okay. Any question about that? Okay, let's make 5 minute breaks because we now will be join the let's say a continuous part about flows, which is the next uh, big argument connected to the coding execution. So let's say 5 minutes of. So just let's say a little remark. Maybe some was not clear by my preview. When we discussed the difference between having the methods in our example here, uh, the one that will be hosted inside the scope, which will be eventually coroutine scope, and the other which will be not, is that in the remember coroutine scope, when you do the composition, the state will be preserved. So if you rotate the device, you will preserve the state, but as you remind, to effectively demonstrate this, you will have to create an activity in which you launch the view and host the view model and stuff like that. So for the sake of being quick, I have not created the activity, but you can test on your own that the method which automatically launch with inner scope, especially this one, the not so better increment, will not retain the state of the counter when the view is rotated. Okay. Okay, let's jump into one of the last, or maybe actually the very last building blocks that we need to comply in creating the Jetpack Composite interface and enable the model view model inside our Android application creation. When I first created the example to you, I told you that yes, you can remember a mutable state of, but if you go with the view model, it would be better to instead resort to some kind of object that will be, and now we will know, will be the mutable state flows, which are a specialization of the more general flows that Kotlin provides you. So, what are the flows and how you have to, let's say, manipulate and conceive them? Well, flows can be, let's say, very high level. You can consider them as just collections or linked list of data that, let's say, instead of, let's say, preserving general semantics. So you can host maybe a list of int which will be different conceptually one from each other, even though they are still some of the same type. These flows will be queues of data which have been stored on the same value in different moments in time. So whereas classic collection and say the most similar type of collection will be a list, or better to say a FIFO queue. Okay, will host data that you explicitly enqueue and eventually are able to access via an index into your queue, access via popping the first or the last value. With flows, you lose this control and just, let's say, assign and enqueue some value. And then you will have some methods to manipulate the intermediate result hosted into the list. Why we may want to need less control of a standard queue? Because you will then delegate a lot of complexity to the method which will be used in a given context into your application, and especially it will be way easier to allow us for asynchronous result and asynchronous computation because flows will be fully compliant with coroutine, or actually are just a sequence over coroutines, we may say. Do you remember sequences or maybe we can quickly grab the slides of, let me just do in a very not the cosine, but the cosine, 0, 1 cosine. Okay. So we have seen that back in the days, one of the first lecture about the different collections, you will have like both list sets, stuff like that with iterable stuff. And also we have seen that you can have these sequences which have the behavior of executing chunks of your eventual list of filter, consumer, swapping, and to operate them lazily. So instead of classic collection in which eventually each of the method will be executed on each instance of the previous one, with the sequences, you will have the behavior that, okay, as soon as you reach some consumer for the sequence, so special methods that eventually for sequences were like to list, you will go to the first, the previous one again, till you reach somebody that can fed as the producer your list of methods. So you go to the D, but the D will not execute on one time all the methods because as the first filter stops, it will not proceed into the execution vertically here. Okay, you reach the quick, which have more than 3 letters, then the other method will be called again and again. This may resemble somewhat what we have seen with coroutines, if you think about, because here you have chunk of execution that maybe can be split and also maybe parallelized in some way. The key difference, in fact, among the, let's say, plain flows and the sequence is that that sequence will run synchronously, whereas the flows will be allowed to run asynchronously, but with the same approach of sequence. So that's the key understanding of bringing for you home. If you understood the sequences, flows are just the asynchronous version of them. When we may need the flow, so just lay down some opportunities and when they will be useful. Where, for instance, when you have to create buffers from data stream which arrives from the web. So maybe you have a producer or maybe some sensor. So you have like a fast producer of data, but you want just to access the most updated values, and you want to do that by, let's say, having some mechanism that allows you to not starve your memory by filling up the queue too much, and also retain the most updated value whenever you have to display it in the user interface. So Flow can help you with that, but also when you have to provide partial results. So, for instance, if you need to filter on a large database or maybe some queues, some queries that you may ask online, for instance, in your project, maybe to ask online the list of travels. It may take a lot of time to retrieve all the data in the to show on the first travel list, travel grid display. From the point of view of a user interaction, a user experience, it will be meaningless to wait till all the data are retrieved and then go from a blank page to a fully, let's say, fully populated page with all the data. Because indeed, the user will start maybe with little chunks, as we remember from the principle of the chunks of memory and working memory. Maybe he will need just to see some data appear and then maybe scroll down. So with the flows, you can actually start showing the um, 4, 5, 10. As soon as the data arrives or the filtering happens, you can start showing something and your interface will result more reactive than just waiting 10, 15 seconds to download the or filter the full list. So that's another way of implementing good UX principle in the from the coding point of view. I just told you that these flows will be executed inside coroutine and from the point of view of jargon and also actual methods that you will maybe use in flows, it says that when a new data is enqueued into this queue of time-sensitive data is actually emitted. So emitting a value into a queue mean into a flow just means to add a value into it. There are, as we have seen for a collection, actually the same set of methods that you will be able to operate on sequences, but in the fashion of the flows, these will be considered as intermediate operators. What are them and what they are, it means? Is that these operators will be able to, let's say, set for you some operation to execute eventually on the data arriving on your flows, but the execution of them is not triggered. So you just, let's say, set up a plan to filter and manipulate your data, but the execution will not happen as soon as you call them. So for instance, you can add or remove elements, you can filter them, you can zip. We will see some of these methods more in details. And there are tons of them. If you go to the documentation of Kotlin and also on the Android, you will see maybe 30 or 40 methods to in terms of intermediate operators. So you can check there if there is someone that fits your needs. Of course, there are some methods that will be more used in the Android world, and we will focus on them. In the another things to remind and to bear in mind is that these methods will separate the flows into two flows. One is the upstream flows, which is the one that let's say you operate your intermediate operators on tune. So the method in which you call the method is called the upstream flows. And then each of them will return a new downstream. So in such a way, every execution will operate on a different flow, which actually is the result of the previous intermediate operators. And when the execution is finally started and triggered, when the so-called terminal operators will kick in. There are, again, a lot of them. Some we already know, like the to list. Some other are specific of the flow word, like the collect or reduce, for instance. When these are called, it means that finally the execution of your plan of manipulating manipulation of data will happen. Of course, they can complete or eventually raise some exception or fail on the flows. And there are also some specific flows which are allowed, so specific operators which are conceived to operate sequentially into your routines, like the buffer, the flat merge. We will see some details later about them. Just to start, let's say, bear in mind that there are some of the flows which may be executed into a coroutine, but it's not mandated. Some others that are better to execute into a coroutine because will allow your concurrency to run smoothly. Okay. By default, the flows will not start to collect data. Okay, so when you instantiate the flow, it's said that you have created a so-called cold flow, which will not produce any value unless you explicitly call a terminal operator on it. There is also another version of flows which instead, let's say, start receiving, start collecting data uh, based on some rules that you may pass in, and you have to convert a cold flow, which is the default state in which flows are, into a so-called hot one. So even though there is no one consuming them, they will listen and they will produce data, emit data inside. The two methods that you will mostly use are the share-in and state-in in the Android world. So these two, especially the state-in, will be one of the most used to convert. Some example of when it's better to use or when it's expected to use a cold flow and one which is expected to use a hot flow. For instance, for the Conflow, you can think about the execution on some resource like a database. So if you do a database query or file reading, maybe you do that by executing just the cold flow because the resource is somewhat static, even though maybe the access is asynchronous and may take a lot of time. Whereas the hot flow is more suitable for live data, like collecting data from a sensor, for instance, the gyroscope or the GPS location, and also for live data coming from the user, so like user UI input events. Let's go ahead. So these are the two main methods that you actually are not supposed to call explicitly unless you want to execute some examples. So there is a collect on the flow interface that will start to, uh, is the basic method to terminate uh, the uh, the plan and initiate the processing in the call flow. And you have also a flow collector, which will be not thread safe and is the one which the emission may happen. Let's see some example of a flow object. And just I want just you to reassure that it will be very rare for you to use the straight plain flow into the Android world. You will use some specialization of it, but just to give you a complete overview, but quick at the same time. So, for instance, with flow and the flow operator that we have seen here, flow collector, sorry, you can emit two values, and this will be encoded into this stream hosting method. So if you, in a given scope of a coroutine, will collect data on the stream, as soon as the collection will start, you will receive and switching among the main flow and the stream inside the flow, and the execution will be chunked. So as you can see here, first the emission is happening, and then the execution of the print line will happen, and we will do that also for the second method because this is a cold flow. Okay, it will happen as soon as you collect and go down to the hierarchy of the plan that you set up. In that case, there is no previous plan to collect, and then just the lambda will be executed on each emission of the data. Some method just to have you general ideas of where you can expect to create flows on. So you can, for instance, derive a flow from an iterator object, from a collection, from an array, from a range, also from a lambda, if the result is, let's say, appropriate. You can straight create the flow like we have done, like list of or sequence of from just a list of elements here. And you maybe are more interested in creating some flow from a suspendable set of methods collector as in the previous example we have exploited. So here are some example of usage of these main methods to create flows, even though we will not use maybe in the Android domain. So let's see the main cluster of intermediate operators that you may want to maybe uh, have a first quick glance onto. So you will still have the map, which is the same of the map of collection. So we'll transform the upstream into the downstream with some mapping rules that you provide via the Lambda function. You can also have the version of the mapping which operates just on the last method, last value emitted in the queue, which some cases may be more appropriate, especially in case of outflows. This will be more appropriate. You can have some filtering. So you pass the predicate here, and as with SIM4 collection, you can filter selectively emit on the downstream. And you have methods that are specialized for the flows. These are not available for the sequence, for instance, which are debounce and sample. Uh, I think that the majority of you are already familiar with the concept of the bouncing, at least maybe the one of you that have programmed some Arduino buttons or also maybe some state transition. Usually you have let's say, two ways to implementing the bounce behavior. The first is based on hysteresis, in which you set basically two threshold, one for entering the process of the bouncing and one for, let's say, absorbing the bounce. If you think about a signal, for instance, let me draw some stuff. Okay. So maybe you have a read signal from coming from a button that the user may want to press. Okay, this is the end of the user. Be creative in. Uh, okay, this is a button. You have a signal, and when the button is hit, maybe you lose the electric signal for some time, and then the button goes up again. If the button is not the best, or if the user doesn't push fully the button, you maybe have some signal goes like that. Okay, but still you want to detect this as a single click. That process that, let's say, cancel out this spurious signal is called debouncing. So either you can, for instance, go by setting two threshold, or one for usually the second click is not as light as the first one for entering the bouncing and one for exiting it. That is one kind of approach. Or you can simply say, if something happened within a given amount of time, just ignore it. So you can either go on value-based debouncing or on time-based debouncing. The one that is implemented into the Kotlin is the time one. Okay, let's clear up. Uh, let's clear for. So here the bounce means ignore eventual collection for a given amount of time. This will be quite useful in the, for instance, when you have to deal with the preventing recomposition based on data coming for UI stuff. There is another version, which is the sample. The bouncing allows you to define a given amount on time. With the sample, instead, you define a sample rate. So you will sample your values. These are mainly used in outflows by giving a sample rate instead of just a delay and wait for the next read. Okay, let's go ahead. Other intermediate operators which are reserved for flows are the flatting, which basically means that you squash the queue, and by squashing you still apply the plan, which is eventually provided by the map, the lambda that you pass here. And there are, let's say, some different entry point to execute this predicate. So you can go for concatenation of the predicate alongside of the queue, or just go from the latest, or merging methods. These are details that you can read on your own. The basic idea here is that you can are able to flatten out all the queue of values based on some specialized plan. And you can eventually also run just on, let's say, special events that happen within the life cycle of a flow. So, for instance, you can just start your processing based on when some values arrive, execute the predicate as we have done on the list for each values, or when the clear is called, or when there are no more values on the queue. So you can specialize behavior by just decorating the plan, and of course uh, you can eventually encapsulate one inside of each other, because remember that each of them will produce a separate downstream flow. You should be already familiar with the zip, which means that you are able to basically have the let's say, if you have two collection of data, you are able to interleave them, so creating a third one, which is a zip of the first two, which receives one item from the top, one from below, one from the top, one from below, etc. And you have also a combine, which is a more, let's say, convenient way in the flow world to do the zip, because it will allow you not just synchronize based on the order. As you can see here, I pick one from the top and one from the bottom, but also to do this zip with the most updated value. So if, for instance, you miss, um, you have one more value here, but you don't have it in the lower part, you have some values that here, the combination will happen not by interleaving them as in the zip one. Oh, so I'm not very practical with that. So it will not interleave by using this and then that value, okay, and then that one, which is the one that the zip will do, but will go like take this one, and then when finally that arrives, put here. So it's also sensitive on the time of the freshness of the data that is coming. But there are, as I told you, tons of them, so you can check the documentation for further specialized reading. And also we have the terminal operators. So we have previewed spoiler for the collect, which is the most classic terminal operators in the flow world, which allows to finally, in terms of, for instance, the called flows, execute the plan. And eventually there are uh, exceptions that may be arise due to the collection phase. There are also single and first, which are ways in which you can access the, let's say, the oldest value in the queue, set of methods that come from the collection board, and also some specialized, and maybe you remind the fold one, and you will have also here in the in terms of terminal operators, you remind that the fold was the most general method to execute, for instance, accumulators and stuff like that. And also reuse is quite used in the world of flows. So to create, for instance, based on accumulators or other specialized operator, your filtering and processing. So that slide is just to give you a visual example of how similar sequence and flows are in terms of defining stuff. These are actually the same snippet of code in which you just replace sequence with flows, and you have to bear in mind just that these will eventually execute asynchronously leveraging coroutines. And by that, maybe you can also cancel, you want to cancel the execution and propagation of callbacks. Okay, let's see some example from the flows in coroutines world. So in that case, you have a simple flow operators, which goes on for each every 100 milliseconds to emit one value. So this means that 1, 2, 3 are emitted with a delay of 100 milliseconds one to each other. And the main coroutine is right here to execute basically and print coroutine every 100 milliseconds. And then the simple collect will finally execute the plan. And in that case, the plan is nothing, it's just to invoke the lambda function and print the data. So if you go into the output log, you will see that the execution will happen of the coroutine and produce values, and the collection will happen not by, let's say, having here printed the coroutine 1, 2, and 3, and then flow 1, 2, and 3, which will like be the behavior that will be expected in terms of sequences. Instead, here, as soon as every value is provided, since you're consuming that barely at the same time, after 100 milliseconds, also the invocation will be synchronous to that. So you will preserve the order of the execution of the collection. Another example in which you may have instead, let's say, more lazy collectors or lazy consumer. In this case, we have like with timeout or null that I remind you is like wait, but not for so long. In that case, we expect that some value will not be eventually printed out. As you can see here, I have not specified the end of this counter. So it will count, the flow is able to count indefinitely. But since we cancel the execution of this coroutine after 350 milliseconds, just 3 iteration bit will be executed. Here you can see another example in which we use the transform operator, which may be useful in some cases to, for instance, go back in time and iterate among the execution of the mission. So here you have a standard scope to execute on this list 3 items, and is a cold flow which will execute with this method as flow. Okay, this will create the conversion from the array to an instance of a flow. We set a plan and we collect after that, and the collection will go for multiplying by 2 and then emitting 2 values. Okay, so if you go here, we have first execution by 2, and then every other value will emit 2 values with some kind of manipulation based on the iterator object. You can check more with more time. Is not, let's say, key to grasp this example. At this time, is just to give you a broad idea of the opportunities that flows allows you. Okay. One very important, let's say, behavior that flows unlocks is to limit the problem of back pressure. Back pressure is when you have like a fast producer with respect to the consumer associated to it. So you may have like your queue grows very fast and maybe also very large in terms of memory. And then you have to decide to clear and cope with the most updated value. There are a set of ways to do that. Also, the bouncing can allows you to, for instance, cope with the problem of back pressure, as well as flattening the data. Here you see just for the sake of example, another operator which is called conflates, which is able to run the producer of the flow in a separate coroutine. So he will also help the scheduler and dispatcher in case you use a dispatcher with multiple threads to better separate also the allocation of the producer to against the consumer, which is instead invoked into the lambda of the collect. In that case, you have just a generation of the same flow with three integers emitted at a distance of 100 milliseconds. Instead, the collection is simulated to operate at 300 milliseconds. So in that case, the first will be collected. For the second, this will not return, but the value is collected because it runs on separate coroutine. And then finally, when the execution after 200 milliseconds is done, you will access the most updated value, which is 3. So in that example, with respect to the to this one, okay, in which you execute all the value, but stop at some time later on, you will lose access to the second value. But maybe in that case, it's good for you because you want to just, when you're able to process it, access the most updated value in the stream. There are two main, let's say, properties or behavior that you have to guarantee into the flow and actually the flow interface must adhere, which is the context preservation and the exception transparency principles. These are needed to preserve the modularization of the code, and especially in terms of code flows in which you can have the upstream and multiple downstream to collect them, but also to let's say, to forget about implementation detail of each flows. So with these two methods, you have a lot of less workload to think about when you have to implement queues using flows. The context preservation means that the execution context, so dispatcher, coroutine, jobs, and so on and so forth, will not propagate to the downstream. So they will reference to the same context at which the first uh, in which the flows was firstly created. There are actually mechanisms to allow also to change, for instance, the dispatcher. So the one that maybe you are uh, more interested when dealing with data coming from maybe a IO and then to use the value and access the data maybe in a composable object, which internally mask the complexity of dealing with this context switching, which are the flow on method. You can think about the method which is coupled with the with context and also channel flows. So this is a specialization of flow which fully encapsulates the context preservation works without you having to deal with it. So when you maybe have encountered during this week while reading documentation channels, these are the problem they are solving of the dealing with tracking the channeling the execution context throughout different methods. Let's see an example in place. So here you have a flow which emits just a line and print the thread in which this will be executed, and then you set up a plan which says just switch and execute the dispatcher IO your your plan, which you have to read from bottom to top, and the others will run eventually in the thread they will execute in. So by default, run blocking will execute on the main thread. So the map, which is just tell me where you are now, and collect. When you do for collect, it will go and execute the upstream flows plan, which is map, which will ask the previous blocks then to retrieve its data. So we expect to see in that case switch to the dispatcher IO for the emission. So emission will happen into the dispatcher IO. So some of the worker thread that are available. Instead, for the mapping, you will go to the old context, and this is expected to be processed in the main. So as you can see, you can separate quite easily the two, but this is just a, let's say, a full example to demonstrate it. You will rarely use this method. You will, as told you, mainly use the method provided by the Android. Okay. Okay. Let's say that these are all stuff that, let's say, maybe trivial to you, but just to explicit them, the exception principle instead tells that you can propagate the collector exception that may arise inside. So in the plan that should be different in 3 points, and then you can catch at the topmost level instead of, let's say, for each intermediate operator, you can just catch at the final operator, or even based on the completion operator that you can access, which replaces the standard finally block available to catch. So in case of flows, instead of catching and then dealing with some fallback behavior, you can instead of retaining the finally, call the on completion method with some lambda, of course, to or scope, better to say. Here you have an example of this principle in play. So you will have a flow which emits three values, and eventually maybe there are exceptions that you want to catch here because maybe compute one will fail. So instead of catching overall the flow, you just use the catch as a intermediate operator, let's say, or in the plan, and then you can eventually collect. And if more exception happen here, you can catch and then on completion handle the dealing with the failure. Okay, as a final remark, maybe some of you already know the Java RX observables, which were introduced as a dual to map the reactive stream of React user interface. These were introduced by guys at Netflix when they start to implement their application in Java Enterprise. And eventually this will be fully encapsulated into the JavaRX packages. So uh, flows are actually interchangeable quite easily with the observable objects. So if you have experience with that, you may find these two signatures quite easy to read. Mono, for those of you that maybe don't know, is like the standard um, cross library to execute managed code inside, for instance, Linux. Okay, so it's like a static class for the sake of example, but not so important here. The basic key take-home message here that you can interchange an observable, and actually there are some implementation that allows you to specify to transpile the code into the Java virtual machine. It's not the case of Android, but in other contexts in which you use flows, it may arise to you. Okay, here you have some more references that you may want to dive in. And I suggest you to have a read at least at this latter one, which allows you to see where flows are used together with animation. We will see in a later class how to deal with animation, but if you are interested, you can start reading this Medium article. Any question about flows? So I know a lot of details. Key take-home message are that sequence, remind that these are sequences that may be operated exclusively in coroutine. There are convenient methods to execute a plan, and then you can either have call flows that execute the plan when you trigger it, or flows that execute the plan whenever new data is available. That's the main key takeaways. See if I told you all the stuff. Yes. So I would say to put in practice with a example in Android that, and then maybe we'll have some little break. Okay, let's create a file with like for example, and I will do that from scratch. My idea is to have like, let me sketch it in some slide with blank space, like that. So I want to create an example in which I have like two text field, and these two text field in my composable will be the content of this text field will be combined into some text here automatically as soon as the user execute and fill in the data. And eventually you can have a button that clear the two field. That's my plan. So, okay. Visual Studio. There it is. So to create a preview of a composable object that demo the flows, and I will create a view model, which is test flow view model that they have still to implement and display screen to show these flows. No, just implement. Okay. Create this tab, create a composable method which use the test flow VM. Okay. And let's start to create this view model. And populate the view. We leave a column with a modifier which takes all the space in the horizontal alignment of center all the stuff and vertical arrangement of center vertically. No arrangement, center. Okay. They want some input field. I know that I like the outlined one. There should be some. Okay. Now I just placed some placeholder values here and label with some one. Need to fix a bit of. Okay. See if at least this is shown before proceeding. Okay. Great. So I said to you, I want two text field. Control D. Maybe you can add some tracer inside, modifier, right? 16 VPs, duplicate, um, move it down, and then show the result on some text, which will be just a result for now, or very combine the two. Material team display medium. Okay, let's say is enough. Otherwise, we will modify it, and then also another spacer, and then button, medium click, and then inside of the button some text, say reset. All the same style will be okay. We go here and then also on the other. So let's see if the stub is working. True. For now is just the stars. Okay, let's go back to the code. So what I want to show here, I want to bind the values of these two text field to user inputs in order to live compile the text field. And to do that, finally, I will be able to use the flows. Okay. So I want to, let's say, host here two values. One by delegating some flows which will be hosted into the vModel, one state, and then to effectively, let's say, perform the execution, you have to call this collect as state, which is a special method that you will be able to access for the mutable state flows. Mutable state flows. Okay, let me contract this code just to show you one thing. Okay. You see something strange in this syntax at this time, which maybe is different from what we have written so far. For instance, in the previous example of coroutine demo, let's take it from the past. Contract this. Old. Okay, let's take this one. Okay, what do you see is different? But well, first thing is that in the view model, you will not use the delegation. It's not the best example, this one, which was another one with the, let me see. Let's just take it. Okay, you see here the main difference. We used to write the variable to host in the view model as a variable and using the delegate of a mutable state of by using the remember, either the remember um, and then mutable state of if we were not inside the view model, we were not inside the view model, but if we were into the view model, we can use also the mutable state of something by using delegation. Instead, here we just assign this mutable state flow to a immutable reference. Why is that? Because the mutable state flow will be an object capable of hosting the uh, the history of the data. So we don't have to every time access inside the encapsulation of this state, mutable state, and ask to retrieve via their getter and setters. In that case, we can just use the state flow to do that. And the delegation will move into the screen flows, which will terminate every time to collect the state. So that's the key point to remind, which is different from the past. And this will be the main conventional approach that you will see also in a lot of professional code that companies you may find in companies. So I want here two states to host the value of the text of the two text field. So I want to compile a second one, so two st, and I do that also for the two, then two st. You are seeing my screen, right? So, yes. So far, so good. Let's bind now this to the text field. So here, instead of having the value, I just bind by the delegation of the collector state for the first and for the second, because indeed here just the state of a string. Collector state is generic, and being string, the state flow, it will work by type erasure. And for the home value change, we will need to, let's say, either use the setter or encapsulate using the hit method. So in this case, I'll go for the second approach, which is slightly more readable. Okay. So you call value and then assign the value that is reported by the on value chain to update the state. Beware that I cannot use a straight delegation here. So I cannot go for one, for instance, like it, or I should be prevented to do that. Okay. Because by default, I will not reassign it. That's correct. I don't want it to be like a var. Because if I do like a var and I do that, I overwrite with text. I will not put one value in the queue. I will not emit one value inside the collection state. So that's another reason why it's better to allow yourself to give an immutable reference to it. So let's go back to the correct one. So one state and then value. We do that also for the two state and then value. Equal it. And then from combine, we should expect some result. For now, I just, let's say, just go for a static version of it, but we will see that it will not work appropriately. Why is complaining? No, I want to keep it. Okay, in the button we can finally say, for instance, em dot reset that may empty the two field by emptying the respective state. Let's move it down. Okay, one stick equal null and one stick dot value, and then also for the sure stick. So far, I should see the two value grows and then eventually reset. Let's try to rotate, and of course you will see that we lose value. That's fine. A better implementation of that for the result will be actually to combine a value, but let's see why it's better to do that. So let's start to analyze where our methods are called. So I will just display the logcat. If, let's just run it again. And display it, I need to some method. Let's do that. I cannot bind it here. Mm. Let's say you have to trust me and go ahead with that. So I will delegate the result to another state, also to hoist and mask better all the state. Okay. And these act as the combination of the two. So the result will be produced as one stick combine maybe then map the values. So the most simple one would be to go for A and B. But if we don't deal appropriately also with the case in which we have just one of the two shown, we will result in some awkward state. Who is complaining? One is one. No, not here. This is not right. This will be collector state times calling state. is complaining because we need to create the final of that to collect finally the process, and we do that by converting in some with the state in some outflows. We can use the view model scope. I will come back to these details later. Okay, just let me write codes that works for now. Sharing started and then Leslie. Okay, then I will log um, as a debug combine code. Yes, proviamo. Combine code and I also combine A and B. Oh, no, it's maybe too much. Okay. No, two. Let's filter the lookup with this line, and we will see when this will happen, the combination will happen. Let's also hit the reset. Okay, we will see that in that case, you have, let's say, a first access to the flows when these outline are created because the first on value change is automatically set and called by the text field. So we'll have a set of the blank value. Then I brought A in the first text field. I know it's very small, but fortunately we are on desktop and not on in the classroom projector. Then I write B, and then something strange happens here. Because when I click reset, instead of going through, say, the recombination straightforward with the plane, I go for an intermediate step in which A triggers the recombination of the result with still the B available there. You may think, well, that's not a big issue, but if you try to start and start typing something way longer, you will see that the number of calls may grow a lot. And this maybe also be not good if you want to, let's say, preserve and mask intermediate states during clearing, as well as saving some computational time. So one thing that you can do would be, for instance, to debounce as a naive method to remove this additional call during the reset. Um, so let's try to do that. I will let me comment this so it will be also share with you in the code. You, for instance, can combine on the first, sorry, so you can debounce, I don't know, for 1 millisecond, which is imperceptible from the point of view of the user, but not from the point of view of the code. And then let's execute again this. Maybe we can also improve a little bit this code to show just A, if A is blank, so the dash will not be shown, just to remove that. If A is blank, just show B. If B is blank, just show A. Maybe I have one else. show that, and if nothing it can be shown, just return one. Let me just compile again. See if it works. Okay. The dash will appear just when you have the second. Okay. So now I have the bounce. I brought A, I brought B, and let's see if it's enough. So in that case, is not enough, or at least to say it may be enough, but we behaved the other way around because we combine the second value as soon as it appears. So we clear the field, which is A in the reset, okay, the one ST, which will we in turn clear A, and just B will be combined, but now will be debounced, and then will be shown just A with a delay of the 1 millisecond. What happens if we move the debounce on the other side of the street? Choose st.debounce. You can make a bet. Meanwhile, still not working. That's because this recombination will took maybe more time that we are able to debounce here. Because also we have a log happening, we have a lot of manipulation and recomposition that will be triggered by updating the value. So in that case, one approach that is slightly better is to debounce as a plan. So let's say put this combination in some fast operation and then debounce on the fast operation as a consequence of it. So also that will not work. Which could be a fast operation to debounce. Instead of going, let's say, with all these methods, we can map the two values into a pair, for instance, A to B. Okay, here I close my combine, you see, and then on this I will execute the debounce and then execute the rest as a mapping operation. Map operation. I have to provide the A and B, which are now to be unpacked, which are passed here. So I still need it, which is a pair to be unpacked. So A and B, which will be passed alongside. Let me put here. And now we should be able to just see from AB to A, B, and reset. As you can see, now we don't have this intermediate line because we are debouncing the full process and we are debouncing a quick operation, which is just, okay, execute the combination on a fast mapping and then debounce it. Can do also more. You can see still works. Otherwise, you can get some unpredictable behavior in the clearance here. Maybe you can just expect one of the two to be fully uh, clear out, and that's about all of the stuff. Some details about the parameters that you may want to populate here in this state-in, which I remind you is a method to convert the cold into an hot flow. So the state-in will need some scope to run. I use a view model scope for obvious reason here, but in other contexts you may want to leverage other scopes. You here have like, let's say, three main strategy to execute. The strategy is to define the when the hot flow should start and eventually stops to emit value. So the lazy is the, let's say, most conservative one, which tells that the emission will start as soon as the first collection will arise. So when this chain will be called from the point of view of this composable object in this example. So when we collect here, you will finally initiate to start collect, and then will never stop. If you want to start as soon as you execute this line, you need to go for the eagerly sharing started state. There is also another one, which is the most, let's say, flexible, but at the same time the most complex to set, which is while subscribed. In that case, you have to define like you can define like a stop timeout, so you can define like you collect about just, for instance, 1 second long after it started, and eventually you can replay the expiring, so like resetting automatically this counter for some longer values. And if I remember well, there should be also another parameter here to um, yeah, you can define the uh, let's say the kind of well, default is the max value. So if you don't override it, you will say that forever. Otherwise, the execution will stop. Okay, and in that case, it should be triggered as soon as you call the method. So it's similar to the eagerly, but also you're able to define some timeouts for your sharing state. But in that case, lazy is more than fine. And that is the just the initial value to fed. So it's like the first emission to start in your queue default value. Okay. Any question about this example? I strongly suggest you to then take these and try to launch into from an activity, so to see how the differently behaves and maybe adapt your laboratory to start using this mutable state flow. It's not mandatory, okay? For the lab 2, you are not mandated to leverage state flow. Instead, for lab 3, you will be. But since in the end you have to deliver the final project, maybe you want to start to implement this way of handling UI responsive data. And this complies also with the example I told you. Light data will couple with hot flows, whereas database data will couple with cold flows. Okay, let's have a little longer break, and we will start a new set of slides from there. Let's say 10:55. We will revise. Okay, 10:55. In the meanwhile, if you have question, you can write here in the chat, and I will reply to them as soon as we start. Okay, let me stop. Okay. And I want to start discuss with you. Tomorrow we will continue just, but at least to introduce the, let's say, the problem, but I should better to say the solution that people before you faced and find out when attempting to implementing the overall architecture of code inside the mobile, but in general inside the world of graphical user interface that displays act as a front end to some backend data. And we do that by exploring the main architectural patterns that you may see, you may found in the Android also with what was, let's say, very used in the past and now it's considered bad practice or at least deprecated, and which are the approaches suggested for now and for the future at least, as the near future, let's say 2 to 5 years. So first of all, I want to stress here that we are talking about architectural patterns, not design patterns. Have you any idea which is the difference between when we talk about architectural pattern and what about design patterns? I know that a question like that is not immediate online to reply, but just to erase the difference. When we talk about design patterns, uh, we discuss about better ways to implement approaches in our code, let's say at code level, at component level. So, for instance, we've seen the observer pattern, we've seen the singleton, we've seen the reactor pattern on the loop handler are ways in which it's better to implement your code in a reusable, reusable way. So the focus is more on reusability, readability, maintainability of the code, and also, let's say, transferring knowledge and separation of concerns among roles and the responsibility of the code. So it acts more at the, let's say, low level of code implementation. Whereas with architectural patterns, we refer to these best practice or even a high-level approach to structure your application and your code, which focus more on the system level of the. Let me just go to this slide and then go back. On this level of details, where is the pointer? Mm, Okay. So the focus of architectural patterns is not to implement the best way a class or something like that, but is which are the best way in which we can address, let's say, company level problems, which may be like software issues on the long view, which is like how do we ensure that the code is maintainable and you can test different part of the code in separate way, for instance, with unit testing. Uh, Also, how your application will grow, will scale, and how to deal with performance, maybe, or with consistency of data among different instances of your application. And by saying that, it means that architectural patterns evolve also not just because of the, let's say, computer science point of view. So it's not just about let's say, you can demonstrate that there is one better way to implement the code, but usually architectural patterns compromise and evolve based on the context in which your application is run, and not the context, also societal context in which your application runs. What we mean by societal? Well, think about the shift of the approach from having your application like having more thick client and then light server towards the approach in which basically we have the front end almost just dummy which host data which are maybe also processed and elaborated on your server, so in a more light client approach or even just in the software as a service model. Of course, maybe some architectural decision that you made when the standard approach of having disconnected application from the web was the main uh, way to go may not stand the time or of the SaaS model. And it can be also constrained based maybe on the company side which develops the application. Maybe in a corporate where you have multiple departments and maybe one department is devoted just to implement the user interface by translating the designer's mock-up into the UI. Maybe you have one other department that take into account instead the business logic, one for the backend and so forth and so on and so forth. Is a totally different way of defining a process for maybe a small companies in which maybe you have one or two people which go full stack developers or better to say unicorns that have to deal from the sketches to the whole implementation. So uh, the idea is that there is not let's say a best architectural pattern that we can demonstrate, but the architectural patterns may fit better in some context. And you may find yourself in switching architectural patterns because of the application complexity. Maybe there are some patterns that works better with and faster with small applications, so application with small views or simple data or simple less code base, and other that which will scale differently, and you need to resort to different architectural pattern because of the context in which you are. Hope this clarifies a little bit the matters of architectural patterns. So just going to the previous slide that I just skipped. They define in a very high level abstract way the arrangement of the piece of software and one of the main, let's say, outlook that an architectural pattern should have is to clarify the separation of concerns about the so-called business rules and the front end. So basically, by business rules, you mean that in a classic application which stands between the data and the user will interact via some graphical interface that eventually will allow the data to flows and be processed according to some business rules, which are indeed also referred the coupling of to the data and the business rules also as business logic, which is one keyword that we already used a few lectures ago. And this separation of concerns will be the main aim that an architectural pattern should solve depending on the specific context in which it's run and the target deployed the target deployability platform in which you expect to run. The main, let's say, historically, if you have a look at the main application architecture pattern in the Android world, since these four guys, the four components were available since the beginning, there was like enforced separation of concerns, or at least enforced pattern, because the components were considered as a first approach to separate, for instance, the notification of events disconnected from what was the graphical user interface. But since we have just seen that the graphical interface is the mediator for the user and the business logic, the other aspect to consider in that case is that activities were considered like a great, the main concentrator of all the application. And that was maybe at the first iteration bearable, but as the complexity of application evolves, it will become a nightmare to operate with just the activity as the main dealer for all the main duties of your application. Maybe you started to see that if some of you have attended other courses back in the days by leveraging standard approach with activities and then maybe fragments which hosted the views layouts was a first attempt to ameliorate and dividing responsibility among activities. It's quite difficult to design, let's say, a medium application like the one, or even a simple like the one you're implementing for your group project by just leveraging activities, because we have a lot of troubles in maintaining the code and also updating it along you are building incrementally your code base. So the key principle is that you must remind is that the approach that you eventually conceive in the world of Android shall be resilient to the OS behavior, which means the the approach of business logic must survive to activities that must be killed by the operating system, maybe be killed by the operating system, and you need to put in place some mechanism, architecturally wise, to preserve and prevent this loss of data. And also, it's a good, let's say, a good way to think to not just depend on the active version of your data, which may be in some case helpful to cache them, but it may be helpful to not just have a direct link from the data that are shown to the user to the one which are hosted. Maybe some mediation will be helpful in guaranteeing that the data will be coherent and updated in the most updated version, both on the device and especially once we move to the SaaS approach, also on the server. Last but not least, one of the main pillars in modern Android is to guarantee asynchronous operation, not just in terms of the graphical user interface responsiveness, but also with the backend execution on a remote server and queries over the web. So as anticipated, one of the first approach was to deploy fragments, which were like sub-views in the activity that you can inject to populate the view. And these, back in the days, acted as classes to that glue. So the activity just acted as gluing different piece of fragments. Maybe if you have opened the JetChat sample that I suggested you, I think last week, you've seen that some fragments will still be there because it was still till 2022, maybe that a lot of compatibility from the Jetpack Compose, which was quite new at the time. I remind you that it was introduced in 2018. Let's say to ease out the migration to Jetpack Compose, there were some fragments as host of also composable objects. But nowadays, this is no more considered as a good approach. Instead, we go with activity that hosts views eventually hot swapping a piece of them. And one way that separation of concerns is implemented is to provide and separate the UI stuff from the so-called model. The model is the solution that is found to encapsulate the data and endow it with some business logic that eventually is interfaced with the UI. So the model is not just the data, but also how the data should be uh, let's say, arranged and also baked or prepared. So the provisioning, the providing of them to the UI will be a straightforward process, and there are no more intermediate operations that the model usually uh, will also attempt to mask the complexity of accessing the networking problems. So which are these states that we are discussing about? And usually you, as maybe a started to implement, will try to preserve the application states but at the same time allow these application states to evolve across time. As we have just um, exemplified in the flow demonstration, we attempt to have some data that will be shown, let's say, permanently in the domain of Jetpack Compose. I remind you that you have always to launch it when you use the view model for the activity. So they will be resilient to the same session of data, but also alive and keep the data evolving once the user interacts with it. Some of them are data that are passing, some of them are events that the user may trigger, so maybe trigger some business logic as we had seen in the domain of buttons, for instance. And the idea is that the state must survive two different, let's say, scenarios. The most basic one is the UI state. So, for instance, you open a hotspot menu. Your application in the profile, maybe I don't know. You have a drop-down list showing, or you have a button that enable to show the history of or the log of travels. When you rotate the device, you want to preserve the fact that the variable which was hosting the show the history will be preserved across the recomposition. So that's one example in which you want to preserve high states, or also the menu of the drawer was open or not. The form, which is what we have seen in the example, so the content inside the text field to be preserved across the session, but also the application state, which means, for instance, you have created your profile, you want to cache it both on your user preferences and also push them onto your backend server. And eventually, you can also preserve the state about read-only data. Think about in your application of travel description. Okay, maybe you want to have some read-only data, which is the case in which you explore the description of some travel which you are not created as a user. So in that case, you want to preserve the maybe the state of the view, in which point you have left. Maybe you are reading the description, you are reading the itinerary, and you switch to your calendar to check the dates. And when you go back, you expect your user to stay in the same point in the application, not to go up in the view and then scroll down to reach the same point, and so on and so forth. So ideally, you should put in place a mechanism to ease out this process for you and not have to every time remind how to keep track of all these action and the state preservation across the different scenarios. I said maybe some data may be hosted on the web, or thinking. So it's another process. So historically, uh, there was just in the beginning the new model view controller. Nowadays, also with the, let's say, with Jetpack Compose, there are more architectural pattern that will be able to provide you a general solution to this problem. And in particular, the most used one in modern Android are the model view intent and the model view model. Okay, so we will see better in details these two in tomorrow. I would like to just introduce at least the first two today. And beware that maybe the model view model name may be a little bit misleading because here you see four letters, so maybe you expect four actors, but view model is just one component. So in all the architectural patterns, you will always have three main components. The model, as you have seen, survived through all the evolution because it's just data with some little logic as ways to preparing your data. You have the views because you have the user interface towards the data. So the main thing that changes is the interface between the model and the view, which may be a controller, a presenter, an intent mechanism, or a view model. Just a quick, maybe spoiler, and we will see that more in details tomorrow. Model view intent usually is better to use when you have small code base and quick and very, let's say, small amount of data to preserve across views, whereas the view model is the most consistent way, is the one that you are invited to also use in your project because it allows you to scale more your code and will be resilient to all the scenarios. Even though if you have a very small code base, it still works great, but maybe it's like killing a mosquito with a bazooka. So in that case, you may resort to the model unit. But let's start to go from the history. And back in the days, regardless of Android, so when Android was designed, it just, as we have seen in many contexts, implemented the stuff that were state of the art at the time. And the state of the art for implementing the architectural pattern of graphical user interface, for instance, in Windows, but also in the Mac OS and on the web, was to go for the model view controller approach. So the model will host the business logic, the source of the data, which will be eventually stored locally on the web, and he exposes some methods to let your data evolve according to the business rules. Eventually, is the entry point to the remote server, as I told you. So if you go through this loop, you will see that there is like just one way in which your data will flow, which is the model is responsible to trigger some event to update the view, which are the ways in which we have seen the three ways to display information to the user. So, and in that case of the view, the new model view controller, that was just the standard imperative views coding. So with the guides, not with the layout and so on. Okay. And the view will be then just responsible to the pick and represent the model to the user interface. The problems were introduced, let's say the solution, but also the connected problem by the controllers, which in this architectural pattern is responsible to, as you can see, act as a mediator, which is nothing but between the views and the model. So the idea was that, okay, the data will fed the view, the user maybe want to update some text field and do some stuff with the data. And then instead of storing them, we ask the controller to transform this user interaction in something that the model can digest. So the controller will call the methods that the model exposes and manipulates the data. That is quite straightforward, quite simple, but it exposes you to a set of problems in terms of making your component grows easily, because it's not easy to, for instance, go for hot swap of a piece of your user interface, especially when you were in the imperative form. but it will totally impossible to support, for instance, the Jetpack Compose way of behaving, so with the declarative UI. Because as soon as you also have some data, so for instance, if the recomposition is triggered, you will totally lose the content, hence you will totally lose the update of the data on the model. So the problem here is that you have a high coupling. The data are there is a lot of code that binds the view to the model via the controller. So a lot of complexity here is in design the controller, which will become very easily not maintainable. These slides should sum up the thing that I just told you. Yeah. And of course, the pros of the model, which is the separation of concern, is quite clear in that case, at least among the three stages of control. And it was a first way back in the days to allow for design unit test, because in that case you can just design unit test for the UI's interface, unit test for the controller, and unit test for the model. So separation is guaranteed, even though there is a lot of complexity hidden in the controller and a lot of complexity on you to ensure that all the process that we have seen will survive to the operating system that may kill the view, hence the data, the most fresher version of the data. So a slight change to this model view controller was the introduction of the new model view presenter architecture. So in that case, the model and the view are as before. So view will host some representation of the business logic, and the model will still host the data with some business logic, which exposes yet methods to manipulate from the presenter, which takes the place of the controller. But as you can see, we don't have here a closed loop. There is not a straight say, duration of events that the model fires on the view. In that case, the presenter acts as a real mediator, which interposes himself between the two. So not just the model updates the view, but goes through firing events for the presenters. So it's like a reactive way to provide updates to the view, which is indeed responsible to digest and call methods on the view to later update it. So in that case, the problem of, let's say, having fresh and updated data is for sure ameliorated because we guarantee that the updates are consistent to the model and to the view, because every time the view needs it to update the model, you can just ask the presenter to update, but also you have the other way around. So the model will ask the presenter to update the view. So every time a new view will need the data, he will always ask the model with the most updated version. Which are the pros and cons of this approach? Is that the separation of concern is still guaranteed as in the model view controller. Indeed, we have just moved, let's say, aside the controller and named it the presenter. But also now, finally, the view and the model are fully decoupled and they can change independently. So also the stability will benefit of that. If in the previous case, a model view component, you will not be able to, let's say, update the view without updating also the other two components, because you have to keep in line all the three. Whereas with the model view presenter, there is another layer of separation which allows you, for instance, if you want to just update the views, the layout, the graphical interface, you don't have to change the controller because the entry point will be the same. So the separation is quite more clear between the two. There is just, let's say, a major drawback that is worthwhile reporting to you. That is The declarative user interface are not easily coming also with the approach of model view presenter because a lot of complexity is introduced in the synchronization process. So we have, let's say, solved the issue of having these two display consistent and coherent data, but still we have to ensure that in the presenter, and that's not a trivial way to do. So I will let these two models sink in and let's start maybe think on yourself, which could be an improvement of the model view presenter, which solves the problem of declarative and UIs. And tomorrow I will go into details of the solution, which is model view model. If you don't have a question, let's see tomorrow in class. So room for tea as usual.